So, good afternoon, everyone. We started last lesson discussing the fundamentals of quantum mechanics, and this lesson we will continue doing the same. So, the heart of quantum mechanics is the wave function, and the wave function has a probabilistic interpretation. That is, in quantum mechanics, we cannot say what is the path of the particle, unlike classical mechanics, but we can gain information on the probability of finding the particle somewhere in space. And then later we will see we can find the probability of measuring the momentum of the particle, etc., etc. So the basic ingredient of quantum mechanics is the wave function. And in 3 dimensions, it is a function of the coordinate of space, and of course it can evolve in time, and its evolution is described by the Schrodinger Equation. Let us now discuss a little bit what does this amplitude mean. If I have a Cartesian coordinate system with some origin, so this is x, y, z, I can ask the following question. I can ask the probability of finding the particle somewhere in space. I can look for it. What is the probability of finding it here? What is the probability of finding it there? So let us assume that we look at some position at distant r from the origin. What do I need to do? I build a small box. The box has a size because the probability of finding the particle in any particular space, if this is a continuous system, is actually 0. I need to have some small box, and I ask inside this box what is the probability. And this box has a volume d3r. What is d3r? It's dx, dy, dz, corresponding to, this is dx, dy, dz. So this is an element of volume. Then the probability of finding the particle somewhere in space is not given by the wave function. It's given by the amplitude squared of the wave function, by this thing. Then I multiply it by d3r, and this guy is the probability of finding the particle in a small element. Small element means in a small box. This small box that I built, the size of it is we think about this as an infinitesimal size, but in practice, let us build this as a finite size thing. In a small element whose volume is d3r in vicinity of some position r. Actually, this is one of the fundamental difficulties in quantum mechanics, and that is that we cannot interpret things deterministically. We have to go to a statistical interpretation. We don't know exactly where the particle is, but we can more or less say where is the density, etc. So this thing, without the d3r, is actually a probability density function. But here I look at the probability, and this means that this object has no units. This object has no units, but this element of volume has units d3r, so this object over here has units of 1 over volume. That's just the units. The square brackets I use here are just to say the units of. So it's 1 over meter to the power 3. Because I'm working, why is it 3? Because I'm working in dimension 3. If I would be working in 1 dimension, the units of this wave function are different. If this is the square of this, then of course the wave function itself, in this example, the units of the wave function is 1 over v to the power 3 over 2. Because here I have this square. the wave function itself is a complex function. It has a real part and an imaginary part, so it cannot be measured directly, at least in the classical interpretation. You can talk. So this, the wave function itself cannot be measured, but the square amplitude in principle can be measured. This is, of course, a real variable when you amplitude square it, and that's why this has a physical interpretation, while psi by itself is only an amplitude, not a real measurable thing. Let us go now to one dimension, and most of our examples at the beginning, let's say the next maybe half of the course will be in one dimension. One dimension is much easier than 3 dimensions, right? So we would solve things in 1 dimension, and the second half of the course will be 3-dimensional. So let us look, let us say that we have a wave function in 1 dimension. It's now a function of x, the position. X stretches from -infinity to +infinity, and time. And this is a solution of some Schrodinger equation. I got it from somewhere. From here, I can construct, I want to know, let us give an example. So this is x, and t is fixed, 1 time. So we're not talking about movies. The psi of xt, I'm taking a snapshot at some given time t. And let's say that psi squared looks something like this, some Gaussian shape. What does it mean? It means that at these locations there is a higher probability of finding the particle, while here the probability of finding the particle is very, very small. Now, I can do a measurement. What will happen when I do a measurement? In what sense is the particle actually a particle? Let us say that I prepare many systems, and this is the density of these particles. And then I perform a measurement, and my measurement is, I ask, where is the particle? It will be somewhere, because a particle is a point particle. It has a mass, it has a charge, and I can locate it. In that sense, it is a particle. So when I perform a measurement, if I prefer one measurement, this is this line here, I will get some location. And I have some error of measurements. That's why I give you some error. Then I perform another measurement. Now, in classical mechanics, I would say if I prepare the system again in the same initial condition and do the measurement again, what will happen? I'll repeat this. But in quantum mechanics, this is not the case. I again prepare an initial state like this, and then the second measurement, let's say, is like this. And then I add the measurements. And it's important that each time you start with the same wave function, I add measurement and then another measurement. And then I have one here and then one here. One here, and maybe I'll get even one here. And if I do it enough times, that is, if I do it infinite amount of times, then I will see this profile corresponding to this thing. But we can't determine the position of the particle in one individual measurement, but the outcome of the experiment is random, and it's given by this probability density. Now, given that you have a probabilistic interpretation, I can ask, for example, what is the probability of finding the particle in some finite size, let's say here, between x1 and x2. So x1 and x2, the experimentalist says, oh, this is x1, this is x2. I want to know what is the probability of finding the particle in here. So the probability that x in a measurement is between x1 and x2. Well, if this is a probability density, this thing, what do I need to do? This is simply given by the integral from x1 to x2 psi x t absolute value dx. So I need to take the lower limit, the upper limit, and I need to integrate because this is a probability density. When I integrate, and that is more or less the area. So let us say here, this is x1 and this is x2. So this area underneath this curve, like in ordinary probability theory, this is the probability of finding the particle in this interval. And of course, when x1 and x2 are close to each other, that is x2 is x1 plus some delta, then this will be simply the amplitude squared times this delta x. That's the probability density. But in this part, once you accept that this square of the wave function is a probability density, then usual statistics holds. And just to remind you, I can, for example, find the average position of the particle. The average position of the particle, you can see here what I mean from a measurement point of view. I measure many times and I want to know where on average the guy was situated. So in this example, the average will be more or less close to this maximum. That's trivial because I drew a Gaussian shape. So what is this thing? Okay, so this is integral from minus infinity to infinity over all space. Now I need to write my probability density, psi xt, absolute value. And I have to multiply by x to get the average value. And this is, by definition, this is the probability density times x. This gives you the average. So the message here, I assume that you learn some course in statistics and that you know how to take simple averages, but I'm just repeating that this is the simple way of taking averages. Now we're going to do something which is a bit strange at the beginning. I'm going to rewrite this like this, psi star, which is a function of x of t, times x, psi, and then do the integral. So what I did here, what is this psi absolute value square? It's psi star. This is the complex conjugate of the wave function. So I just say psi star psi x, and I just want to put it here. And you will see later why this is more general, because when I use other averages like momentum, you will see here the momentum operator. So in textbooks, many times you will see either like this or like this, but it is of course the same thing. Okay, now we can have many situations, of course. First of all, I don't need to restrict myself only to the average. I can calculate the fluctuations. Because in some sense in this picture, what is the difference between a quantum particle and a classical particle? A classical particle, you can think about it as some function that has a wave some particle that has a wave function, but this wave function is very narrow and located somewhere in space. That is more or less a classical particle. Of course, there's always detection problems, but a classical particle has a position. So it means its distribution function is very peaked and very, very narrow, like a delta function. So the quantumness of this object, this simple object, is the fact that it has some width, the fact that you can measure different values. So naturally, one would like to calculate it or characterize it. So this you can do, for example, by calculating not the first moment, because the first moment gives you the average. I'm going to calculate the second moment, that is x squared average, and that is given in the same way as before, psi star x squared psi dx, which is of course the same as writing the density times x squared times dx. Calculating these integrals can be a nasty job. If you have a wave function, you can either calculate it analytically. If it's a Gaussian, you can calculate it. If it's not a Gaussian, it might be difficult, but you can do it on a computer, etc. Now, the width of this thing, or the variance, is given as usual by x squared minus x average squared. So in this example, if we call this guy here 0, that is the origin, is exactly on the maximum, that is our definition of our coordinate system, Then, of course, in this example, if this would be a symmetric thing, then the average would be 0. The particle is located averagely on 0, but the variance is given by the second moment exactly. But generally speaking, of course, you can have a shift or whatever, so you need to subtract the average to get the fluctuation. So this is the fluctuation in the position of the particle. This enters in the uncertainty relation of Heisenberg that we briefly mentioned in the previous lesson. This is the uncertainty in the measurement of the position of the particle. If this would be 0, then it would be classical in the sense that you can say, oh, here the particle is with complete accuracy. The fact that it's not 0 is already a quantum effect. Okay, so now you should also recall that the wave function doesn't have to look something simple like that. It can look maybe something like this. As a function of x for some t. So this is very non-classical state. In what sense? Or why is this? Okay, this is also quantum, but slightly quantum. Because here at least the average is well defined and the most probable measurement is the same as the average. But for example, if I measure here the average, what is the average? If I call this point 0 along the x coordinate, and these two guys are symmetric, what is x average? It's exactly here in the middle. But this is the least, or one of the least likely measurements of position. So the average doesn't really tell you much. The average is not where the particle is, because most of the time you will find it either here or here. So if you perform a measurement here, you prepare a system at this state and measure position, then you will see something like this. Then you'll see up. Then slowly you'll build up this histogram, which in the limit of infinite number of measurements will give you this shape. If you have a few measurements, you cannot say where the particle is actually is. So one measurement is not good enough. So now we want to discuss some properties of the wave function based on the Schrodinger equation. So let me briefly remind you, what is the Schrodinger equation in one dimension? The most economic way to write the Schrodinger equation is with the Hamiltonian. So the way I write it is the time derivative of psi equal h psi. This is a nice economical writing in the following sense, that if I want to be more specific, this is h bar, so I need to specify what exactly is the Hamiltonian. The Hamiltonian is the combination of the kinetic energy plus the potential energy of the particle. So I think about first of all, I think about a particle. So I have some v of x. This v of x can be even 0, or a constant. But let's draw something. This v of x, its derivative in the classical world would be simply the force. So this is the potential acting on the particle. Of course, you need to tell me in advance what is the forces acting on the particle. So this is, given one system, let's say it's harmonic oscillator, other thing, it can be many things in the Coulomb field, etc. It can be the Coulomb potential in 3 dimensions. Many potentials are known from first principles. Okay, we have some potential. So H, I write it with this hat, is an operator. In what sense is it an operator? You see, H is acting on psi. It is something that is doing something to a function psi. That's why we call it operator, because it's operating on something, on the wave function. And h is given by p squared over 2m plus v of x. So here you see the kinetic energy and the potential energy. But the kinetic energy is given by also an operator when we identify the operator associated with the momentum. This was done already last lesson, with this operation, minus IH d over dx. And again, it operates on something, on the wave function. So when I square this, I get here minus h squared d over dx squared 2m plus vx. So the kinetic energy is very different object if compared to the classical kinetic energy. The classical kinetic energy is some number, and here it is an operator, this object. One property of the Schrodinger equation, which is important but also trivial, is linearity. So the Schrodinger equation is linear. What do I mean by that? The potential doesn't have to be linear. What I mean is it's linear in the wave function psi. So there's no psi square in the equation. That is very important because this allows me later to solve this equation. It's not too complicated to solve the Schrodinger equation. It's a linear equation, and from here you have something which is called the superposition principle, which is a big name to something very simple. And the superposition principle is related to the fact that you have a linear equation, and this uses something that you already saw, let's say, when you studied waves. So you know that you are in the wave equation, where you have the second derivative of x and the second derivative of time. You take a free wave, you can add many waves together, and these are still solutions of the wave equation. And similar thing happens here in the following sense. So the superposition principle is the following. Given that psi1 x of t and a different wave function psi2 x of t are solutions of the Schrodinger equation, so is C1 times psi1 plus C2 times psi2, where C1 and C2 are some constants which do not depend not on time and not on space. So if I know one solution, I can, and I know another solution, somehow I can add these solutions and this will remain a solution. And one example will be free waves. If I have one free wave and I have another free wave, one of them with momentum k and another one with momentum k prime, the sum of the term of them will also be a solution, so I can construct wave packets. This will be done later on. To show this is trivial, but let us do this because the technique is also similar to what we're going to do later. So all you need to do to prove this is just you take, I'm going to call all this guy, this big guy, big psi. So how do I prove this? I just have to take this psi and I have to put it into the Schrodinger equation and just check that this guy, which is a combination of these two guys, is a solution of the Schrodinger equation, given that these guys are the solutions of Schrodinger equation. So I need to take I, and this is the big one, the sum of the two. This dot is the derivative in time, which is the same thing as d over dt here, just it's a shorter notation. Dot is much better than d line. Here you have 4 symbols, here I have 1. So this is a good symbol, dot. It's a time derivative. This is equal to IH C1 psi1 dot plus C2 psi2 dot. So I just took the time derivative and I used the fact that C1 and C2 are constants independent of time. So when I take the time derivative, this operates only on these guys. And this guy, because IH psi1, what is IH psi1? Well, it solves the Schrodinger equation. This is my assumption that psi1 and psi2 solve the Schrodinger equation. So this is equal to C1 H psi1 plus IH. IH, the derivative here is simply C2H psi2. But what is all this? I can put this C2 and C1, because it's a constant, I can move it into the other, in front of the Hamiltonian. Because the Hamiltonian, it contains any derivatives, but I can put a derivative here, a constant here or there, it doesn't matter, because this derivative doesn't operate on C1. In other words, C1 and C2 are independent of position now. So I can replace their positions, and then this is simply C1 psi1 plus C2 psi2, and this is equal to H psi. And this means that the time derivative of psi is equal to H times psi multiplied by the usual IH bar, and that means it's a solution. So we have proven this simple principle. So we saw, for example, for free particle, I had psi1, for example, was I kx minus omega k t. That is the solution of the Schrodinger equation, where omega k, you have the dispersion relation specific for a free particle. Free particle means a particle with no potential. There's no force on it, or the potential is constant. And then I can have psi2 ei k prime x minus omega k prime, a different k. So this guy has momentum h bar k, this guy h bar k prime, and the combination of these two waves is also a solution of the Schrodinger equation. So we can have interference. So this is how you build interference. You take one free wave, and then you add another free wave, and then you can have a combination of two waves which will can interfere constructively or destruct each other. Again, we'll see examples later. Okay, the next thing I'd like to study is conservation of probability. Or you can call this also the normalization problem. Or more correctly, conservation of total probability. We said that in one dimension, psi squared is the density of particles, or the probability density of particles. And if I integrate between x1 and x2 over the amplitude square, I get the probability of finding the particle. What will happen if I integrate from minus infinity till infinity? What do I need to get? 1. And the reason is very simple. The particle is somewhere. It exists somewhere on the nature. So when I had these curves, let's say something like this, the area underneath this curve is 1. And this has to hold forever for us even to interpret the meaningfully this as a probability amplitude. Now, the solution of the Schrodinger equation doesn't have to be normalized, because if I multiply I have this equation, I find a solution. I can multiply it by some constant. It's also a solution. So what you need to do is you need to normalize your wave function at time t equals 0. So we assume that at time t equals 0, the integral psi squared dx is 1. What we are going to show is that if we start with a normalizable wave function, and we will always start with a normalized wave function, otherwise all we do is nonsense. So if this is valid at time t equals 0, then we can have that this thing holds for any future time t. It holds forever. This means that you have conservation of the total probability, or the normalization is conserved. You start with something normalized, it's normalized forever. This fact, what we want to show is that this is a property of the Schrodinger equation. It's not obvious. Not every equation which is linear will have this property, but this is a property of the Schrodinger equation, and this is, if this would not hold, then I would say you cannot interpret psi squared as a probability density. Yes?
What if the potential energy depends on time?
Everything that I'm saying right now is valid also for a time-dependent potential. All this conservation of probability, all this linearity, I did not use in this proof anything with respect to the fact whether h is depending on time or not. You can easily see this from here. So now we are discussing very, very general properties. Time or independent. I'm only, to have some classical interpretation, I'm only using the fact in the background, but even that is not really used, that the derivative of v of x minus the derivative in space of v of x is a force. But this is general. Okay, so I want to prove this. How will I do that? Well, what do I need to do? I need to use the Schrodinger equation. How will I do it? Okay, we will prove that d over dt is equal to 0. If the integral over the density is some constant, independent of time, then this time derivative is 0. So if you started at time t equals 0 with this thing being equal 1, it means that it will be 1 forever. So it is enough to prove that the time derivative of this guy, which we will always take to be 1, is 0. So again, if I start with 1 and this time derivative is 0 for every time t, then this is 1 forever. Okay? So this is our goal, to prove this. So let us do this. It's not difficult, but these type of proofs we use all the time. So I will use IH d over dt integral from minus infinity to infinity psi xt absolute value squared dx. Let us check what it is, and of course I put here IH bar because that enters in the Schrodinger equation. I know that this is replaced eventually by the Hamiltonian, and that's what's going to do. Now I can take this time derivative and I can put it inside the integral because the integral is over x. No problem here, and then I have the time derivative of what we have in here. So this is IH integral from minus infinity to infinity psi star derivative psi, because psi absolute value squared is psi times psi squared. So it's the derivative of psi plus psi complex conjugate psi derivative all this dx. Now if I look at this equation, I see, for example, IH psi dot. What do I know that IH psi dot is? It's H times psi. But I also have here IH psi star. Okay, but it's not so difficult. Let us now see what is IH psi star. So to do that, let us go back to the Schrodinger equation. I have the time, this is the Schrodinger equation. If I take the complex conjugate, I get I turns into minus I, H bar, psi, derivative in time, it's complex conjugate of this function psi star. This is equal H star, the operator H star, psi star. An important property of Hamiltonians is that H star is equal to H. All the Hamiltonians that we know of are like this. It's actually something what you might say even trivial, because what is H? This is p squared over 2m plus v of x. The potential, because it cannot be complex. Why cannot be complex? Because this is related to the force that you have in classical mechanics. So this thing is real. Also this guy is real. It's just the second derivative in space. So it's trivial that from here you get that the Hamiltonian complex conjugate is equal to itself. So if this will not happen, what would you get? You would get a violation of this rule. So this is impossible. That is, the particle cannot be, it has to be somewhere, so we always work with this H star equal H, and anything else is not acceptable, at least in this class. Okay, so we have here two equations, and you see this is the Schrodinger equation, and this is the complex conjugate of the Schrodinger equation. They're very similar in some sense, because the only difference is here you have a minus, and because H star is equal to H, then I can write minus A IH psi star dot, I don't need this star here, psi star. Let us go back to this equation. Why did I do all this? Because here I have IH psi star. Okay, what is IH psi star? It is minus H psi star. And here I have IH psi star. This is H. So, if you want to remember where it started from, let's call this equation 1. So from 1, I get, let's call this I1. All this junk is I1. Remember, what do I want to prove? That I1 is 0. So this I1 is equal to integral from minus infinity to infinity minus h psi star. This, again, I replaced IH psi star. IH psi star. I take this minus to the other side. This is this minus psi plus psi star. And I have IH psi time derivative. That is again H psi. All this dx. Now you notice that in this expression I have these brackets. These have, what would happen if they are super important actually. Because H, what is H? It contains the kinetic energy, the second derivative in space. So if I just delete this, what would this mean? That the second derivative in space would act both on this and this. This is not what I mean because here I have the time derivative here. So what I mean by these brackets is that the H is operating on psi star only. And also here H is operating only on psi. So and this will become more and more clear later, that the order where you put the operators, they are not commuting. You cannot just change things. You have to think a little bit what exactly this means. So this guy is only acting on this and not on this. And this should be clear from this time derivative here. Okay, so now I look at this thing. So let us do it. Then I have an integral from minus infinity to infinity. Here I have, okay, let us write the Hamiltonian. It's the momentum plus v of x. I write v of x, that's an answer to you. This guy is sleeping now because I'm too lazy to write t, but you can write also t. Okay, so this is operating on psi star. Actually, you need two of these guys already. Psi plus psi star. P squared over 2m. This is an operator. This is this h plus v of x psi, all this dx. Now, immediately you see what happens to the potential. You have v of x, psi star, psi. And I made a mistake. You should have corrected me. Here's a minus because of this minus. So this is minus the Hamiltonian. So here I have v of x, psi star, psi, dx. Here I have v of x, psi star, psi, but with a sign plus. So everyone should be able to see that this v of x will be canceling this v of x. And what I'm left with is, I can take the 2m outside, integral from minus infinity to infinity. Here I have minus p squared psi star plus times psi star p squared psi dx. Now what is this p squared? You remember what it is? What is p squared? It's minus h, the second derivative of x, because p is minus h d over dx. So p squared is minus h squared d over dx squared. So what do I have here? I have here a second derivative in space of psi star times psi. And here I have a second derivative in space of psi multiplied by psi star. So one time it's acting on the psi star, the other time it's acting on psi. So what do I want to do? To show that it is zero, how do I proceed from here? What is the well-known trick here? What? Yeah, of course they are equal, but how will I show that? I told you already they are equal. What?
By parts.
Yes, אינטגרציה בחלקים. integration by parts, which means essentially here you have the second derivative of x. I'm going to take this operation and move one of the derivatives, or both of them, I'm going to move over to here. I can do it on both of these guys, or I can do it on one of these guys. I'm going to pull it over by integration by parts. So, for example, I can use let's look at the, what do I want to look at? It doesn't really matter. So, aside, what is p squared over 2m? I'm looking at the second term, at this guy. Psi star integral dx. So this is this guy. This is, let's do it a little bit slowly. That is psi star h squared over 2m. These are constant with the sign minus. Second derivative, that's come from the momentum operator. Psi integral from minus infinity to infinity dx. Now I integrate by parts. Integration by parts. The integration by parts contains two terms. One is that I can take this derivative and take it over here, essentially, and then I have the boundary terms. So we're going to forget about the boundary terms, and soon I'll explain to you why. But this guy, after doing integration by parts 2 times actually, so when I do it 1 time, I'm going to take the derivative here and put it on here, right? And then I'm going to do it another time, I'm going to do it on here. And if you remember integration by parts, each time you do integration by parts, you get 1 minus. Minus and then another minus. So if I do it twice, I don't get a minus. And then this guy is equal h squared over 2m, second derivative of psi dx. As it's by parts to the power 2. Do it 2 times. But what is this guy? This is simply the same as this. Because you see here, what is this guy? This is simply with the opposite sign. This is simply 1 over 2m p squared, because of the minus here and the h bar, p squared psi star psi dx. And you see here I have it exactly with the minus. So this cancels. Where this had 1 chupchik and this guy has 2. So to summarize, I get what I wanted. Okay. I was lucky more than smart. No, that was stupid. So to summarize, I get what I wanted. I get that I1, which is the time derivative of this thing that we started with, dx is equal to 0. So we have proven the conservation of probability if wave function is normalized Normalized, I mean normalized to unity, that the integral over this thing is 1. At time t equals 0, it will remain normalized forever. This is called conservation of normalization, conservation of probability, whatever you want to call it. Now, we added a slight assumption, and that was the boundary conditions in space. Where did I have these assumptions? When I did the integration by parts, because I threw away the boundary conditions. Because I had this integral from minus infinity to infinity, I did integration by parts. I didn't take into consideration the derivatives and the wave function at the origin. However, it is pretty obvious that psi at plus minus infinity at all times t, if you start with some localized wave function, this is always 0. And similarly, you can show that the derivative, the first derivative at plus minus infinity is always 0. To say it differently, let's say you have a Gaussian wave packet of a free particle. You started somewhere like a Gaussian. At the moon, the probability density of finding the particle is 10 to the minus 1,000, which is nothing. It cannot propagate very fast to the boundary, and therefore in the boundary conditions, if you start with something reasonable, normalizable, and within some domain, your particle is somewhere within some domain, then at infinity it cannot be found, not now and not forever. And this is a boundary condition that we added here, because what would it mean that if you have some boundary condition at the infinity that you have some psi? It would be like injecting particles into your system or something like that. So the boundary conditions in space are always in such that they are 0 whatever problem you solve in quantum mechanics. So what did we study here? That's a brief summary. One, we studied the superposition principle and the physical meaning that will soon come. We can construct wave packets. This comes because the Schrodinger equation is linear. We showed that there is a conservation of normalization. And what was the real physical meaning of that? Or why does this happen? This is because H is always equal H star. So the Hamiltonian is a real object. We also studied what is psi squared. What is psi? It's an amplitude. And we got first glimpse at some simple moments. Later we will see that what is the average momentum and things like that. So now we want to ask the following question. We have the Schrodinger equation. And then the question is, where is classical mechanics? Where is the Newton's equations of law? What is the connection at all between the quantum world and the classical world? Because if I just looked at the Schrodinger equation, if you just look at the Schrodinger equation, it will be very difficult for you to imagine that this is have anything to do with classical mechanics. So the question is, what about classical mechanics? So I'm going to give you the answer, and then we'll prove half of it. you can use the Schrodinger equation for any potential and prove the following theorem, which is called Ehrenfest Theorem. And Ehrenfest Theorem says the following. I can take the average of x. The average of x is depending on time, and it's given by what we discussed before. If you have the wave function, you can calculate the average of x in principle. And I can take the time derivative of this. This guy is going to be equal to P over m, where here I'm denoting the average of momentum. So what do you see here in this equation? This equation is something you learned long time ago, and which is that the average momentum, or the momentum in classical mechanics, over the mass is equal to the derivative of x. And what is that? That is simply the velocity of the particle. So in classical mechanics, we have from definition x dot equal v equal p over m. And then you have the Newton's law, which is the derivative now of the average momentum, because the momentum, like the position, is not well defined. It's also a stochastic variable. It's also random. So, but you can have an average over it. If I take this, this is going to be equal to minus what you can guess nearly, the average of the derivative of the potential. And this is, of course, Newton's law. The change in time of the momentum is equal to the force field. F equal ma. Well, here it's a bit more general. I assume all the time the mass is fixed. The mass doesn't depend on time. So the derivative of the change in momentum is equal to the force, but it's not exactly the classical equations. They are called Ehrenfest equations or Ehrenfest theorem, because now we are only dealing with the averages. So average quantities nearly follow classical laws, but this doesn't say anything on the fluctuations or the quantum fluctuation. But on average, we more or less behave in a classical fashion. This you can find in any textbook, for example, Cohen-Tanucci. You can read about these laws a bit more. Now we're going to prove part of it. And actually interpret what does this object mean? What is the average P? What does this mean? And this you will see from here. So let us say I want to know the change in time of the average position x. I want to essentially prove this equation. So I need to take the time derivative of the average of x. But what is this? This is the time derivative of psi star x psi dx. Because this is just the definition of the average of x. This is the meaning of these brackets. These brackets have this meaning. So luckily we have brackets. We don't need to write usually this long expression. But this guy and this guy is the same thing. Now I can always take the time derivative, put it inside here, and this contains two terms, integral from minus infinity to infinity. Psi star, the complex conjugate of psi, the time derivative, x psi, plus the time derivative of x. X is just an integration variable. I don't need to take the time derivative if, but psi depends on time. So psi star x psi dot all this dx. Now I look at this, and because we did already a similar exercise in previous lesson, I see here psi star dot, and I see here psi dot. What is this? What is this related to? It's related to the Schrodinger equation, because the Schrodinger equation tells you what is the change in time of the psi. This is related to the Hamiltonian. So what we're going to do now is replace these two guys with what we know from Schrodinger equation. So we did this already, so just to remind you, minus IH, because here I have psi squared, a psi complex conjugate. So here I'm taking the complex conjugate of Schrodinger equation, so I have the minus here. And here I have psi squared. I'm using the fact that H star is H, which we saw previous time, times psi star. So from here I see that the time the psi star dot, which is what I have here, is equal to H psi over IH bar with a minus sign. And similarly, psi star, this comes directly from Schrodinger equation, but you can simply take the complex conjugate of this equation. What will happen if I take the complex conjugate? You see here I have I star. The I star will be minus, and this will turn into plus. So it's H psi over IH. And this is, of course, Schrodinger equation, but usually you write this IH on the other side. Okay, so now what I need to do is I have to plug in this expression, these two guys, and then I'll have the Hamiltonian inside this nasty equation. Okay, so let us see the time derivative of the position is equal to the integral from minus infinity to infinity. And where does the integral come? It simply comes from the fact that the psi square is a probability density, so to get average x, I need to integrate. Here I have psi star, so this is minus h psi star I over h. And I have again these parentheses. These are super important. This just means that h is only operating on psi star and not operating on everything else. So you cannot just leave this out. It's not like multiplication of numbers. These are operators. So this guy operates on psi star, but now for the time being, not on these two guys. Because here I have the time derivative. Then I have psi star x, because I'm looking at the average of x. This is where it comes from. And then I have psi dot. This is h psi I h. Then I have to integrate over all dx. Now, in H, we have a kinetic energy term and we have a potential energy term. What will happen to the kinetic energy? Because you see here, this is H, p squared over 2m plus Vx. So what will happen to the potential energy? You can easily see that if I have here potential energy, here I have a minus, and here I have a plus, but it's just multiplication of three functions. V of x, psi, four functions. V of x, psi, star, x, psi. And here I have V of x, psi star x, V of x, psi. And these will cancel, obviously. The only thing I have to consider here is the momentum. So if you don't really see this immediately, just plug in here the full expression with the potential and then see that the potential energy will cancel out. So I just write it down here. Potential energy cancels. Because here I have a plus and here I have a minus. And that was because once I took the derivative of the complex conjugate and once I took the derivative of the real of psi. So I have to only consider the momentum operator, the kinetic energy operator. from physical point of view, why is it not surprising that V of x goes away here? Because you know the answer. The derivative of the position is just the velocity, and that is related to the momentum over the mass, right? You know the answer. So, of course, here there's no potential that enters. So that's why it makes complete sense that this does not depend on the position, on the potential energy. So now I have, after I realize this, I can write it like that. And then I can write here, I have IH bar and IH bar. So let us take this outside, IH bar. And then here I have integral from minus infinity to infinity. This is the kinetic energy, which comes from this H. Psi star x psi plus psi star x p squared over 2m psi dx. And the whole Kuhn theory is that, Kuhn is a word in Yiddish, I think. A p square is operating here on psi star, while p square is operating on psi here. And then this guy are not canceling automatically. So we need to look what it means. But what am I going to do now? You see here I have the p squared. The p squared is the second derivative in space, proportional to the second derivative in space. So what do I need to do? I want to cancel some terms. This is going to be the trick that we had before, integration by parts. I just want to move this operator, for example, instead of acting on this guy, let us move it from here by integration by parts and let it act on this guy, like you have here, and then something will cancel and something will not. But that is the simple strategy. So it's pretty simple. So let us denote now, for example, this guy by these two lines and one line like that. And let us look actually now, we're going to look at this guy. Not exactly, so let us look aside. Just do some math, very simple math. The p squared is proportional to the second derivative. So let us look first at what is the second derivative of psi star. This is from here. Times x psi dx. This is not equal because you have the minus, I have IH bar and 2m, but I just take the second derivative because that is what is going on. Now, if I do integration by parts, I have to take this guy twice over here, right? Because I do it twice. So I do it by integration by parts twice. So I need to take this derivative and operate on this guy, and the minus each time I do integration by parts, do it twice. Now, if you're not familiar so much with integration by parts, you should do it slowly by yourself at home. Not like I do it here, because you should check all this if I don't make some mistake, etc. But I don't want to bore you too much, so we're going to do it very quickly and very roughly. So what I really want to do is, because I essentially move this to here, what I really am interested in the second derivative of x psi. And that is equal to the first derivative of psi plus x, the first derivative. And that is equal to psi derivative, but times 2. Because then I have this guy, and then plus x second derivative, where these lines are d over dx. So dot is a time derivative, slash is derivative in space. So if I use this, I go back, so there is some algebra here. So I have to take, I move this derivative here, and then I'll get two terms. And one of the terms is going to be integral from minus infinity to infinity psi star 2 d over dx psi. So again, I'm using this trick here. And then I have another term, which is integral psi star x psi second derivative dx. This guy is exactly like this guy, because you hear I'm not doing it completely. Here you have the second derivative acting on psi. If you check carefully the sign, these two guys will cancel. So what will remain is something, only this guy will remain. So this guy, this cancels. And this remains. The simple story is very simple. You have the second derivative here. If you just move it, you'll get one term, which is the second derivative here. And because this sign is different than here, this will cancel out. But because you also operate on this x here, then you have another term, which is proportional to this, this term. The first derivative of psi. So one term cancels, but you have another one which goes here. So let us just summarize all this. I'll just copy this, and you will check it in your at home. So what do I get? I get the time derivative of x is equal to 1 over IH integral from minus infinity to infinity. This is because of the average, dx. Psi star, because I moved the derivative from psi, I moved it to the right. Then I have 2 h bar over 2m d over dx psi. That's it. Now this looks a mess, but let us just remember, where did I get the 2 from? What is this 2? This downstairs 2 is from the kinetic energy. What is this 2 here up here? That's from the derivative. The second derivative gave me this 2. It was just here on the blackboard. And here I managed to get only first derivative, because one derivative, what happened to it? It acted on the x, and it canceled it. And the second guy is acting here on the psi. So I get this expression. So what does this look like? Well, first of all, I can cancel the 2 and this h bar. And this 1 over I is minus I. This you know, I guess. I just multiply by I upstairs and downstairs, and then I get this guy. So I can write this in a very nice form, or for me at least it's nice. Integral from minus infinity to infinity dx psi star minus I h d over dx psi. But now I say, aha, what is this guy? What is this object inside here? What is it? Not Hamiltonian. Yep. Operator of the momentum. This is by definition the momentum operator that we defined previously. So what do I have here? I have here, this is equal to the integral from minus infinity to infinity dx psi star, the operator p, psi.
But how do we know that this is the momentum?
This we
define, but
this is a very good question. Am I now dealing with definitions, or am I dealing now with interpretation, or am I dealing with a rigorous proof? I am not proving rigorously that this is psi, but I'm interpreting that this operator has an average value And when we will summarize all another half in the middle of the semester, that is roughly chapter 3, you will see what are the assumptions and what are the consequences. So in quantum mechanics, it's not true to say, like in Newton's equation, like 3 laws of Newton, you have 3 laws. But let's say from the dynamical point of view, you have the second law of Newton. Then, okay, given the second law, you understand more or less what's going on. In quantum mechanics, it's a bit deeper than that. You need to interpret what are the operators. And you need to understand how you quantize the operators. Okay? And here I'm just trying to explain, or I see something beautiful, that the momentum operator that we had already in the kinetic energy is not only something that I take the second derivative in space in the Hamiltonian acting on psi in order to solve the Schrodinger equation. It pops out here again. And if you do it for other observables like orbital angular momentum or many other h, you will see the same thing happen over and over again. And then after some time you see it more often, then you will say, okay, this is the meaning of the average momentum. Now you can also say it in the opposite way. There must be some connection between quantum mechanics and classical mechanics. If this would not happen, then classical mechanics would not be correct. That is impossible. I mean, we always, it's okay for us to extend classical mechanics, Newtonian mechanics, into quantum, but you must not completely wipe out what Newton, because that means that what you studied for maybe more than 12 years in high school and 2 years in university is rubbish, which is impossible. So you must have a correspondence, and then you know that this guy, I've forgotten a mass, of course. This is, of course, wrong. Here I have a mass.
The mass is there in the other side. No. In the right, you wrote it.
In the right?
No, a little more to the right.
Oh, yeah, here I have it. Sorry, yeah, here I have the m, but here I forgot it. So, and here I need to divide it by n. Anyway, so to summarize, we see, or it becomes more reasonable now, or it is a proposition, as you wish, to identify the average momentum is given by psi p psi dx. And this is why at the beginning of the previous lesson I wrote the average of x as psi star x psi, because every operator actually, if I have an operator, it will be given by psi star a operator psi dx, at least in this representation where the wave function is written in position space. For example, what is the kinetic energy in quantum mechanics? Averaged. So, on the one hand, the kinetic energy turns into an operator when we put it into the Schrodinger equation. That's p squared over 2m. But I can average it. And then I can get the average kinetic energy, which is simply p squared average, which is the second moment of the momentum. So this guy is simply given by integral psi squared p squared over 2m psi dx, etc., etc. Or I can look at the variance of momentum before I had variance of position, and that is equal to square root p squared minus p average squared. And the meaning of this is I have to calculate the wave function. I have to calculate p squared. I have to calculate the average p, which is proportional to the average velocity. Take the derivative. This gives you the uncertainty in the measurement of momentum. So you measure momentum. You can measure position. You can measure momentum. If you measure position, you have some uncertainty. That was the variance in the position. If you measure momentum, you have uncertainty in the momentum, and this is given by this expression, Of course, this is just the variance. It's not the full probability density function of the momentum. Soon we will see what is exactly the wave function associated with the momentum. Up to now, we worked with a wave function, psi, that depends on position. But there is actually a wave function that is giving you the amplitude of measuring the momentum. Soon we will discover it. But to summarize this part of the Ehrenfest law, what I showed, let us go back to Ehrenfest. So what we showed is the derivative in time of the average position of the particle is the average momentum over P over M. And I said, and this I will not prove, but you will do that, either at homework or if you are not lazy, you'll do it tonight. This is equal to minus the derivative, the special derivative of x. It could depend on its own time, but I only write the position. How would you prove this type of thing? Well, you know it, more or less. You understand how to prove. You have P. So this is P average. Forget about this 1 over M. I need to take the time derivative of this. The time derivative of this will give you here a time derivative and here a time derivative. And then you'll have a time derivative, a time derivative of psi, and psi star, what is that? That is essentially the Hamiltonian times psi. You'll plug in the Hamiltonian, you'll do integration by parts, and this time what will come out, instead of this x disappearing, you will have a derivative of the potential. More or less you can see it, but you really have to do it by yourself to really live this thing. And because one of the technical points here is to be very careful with the order of the derivative. The derivative operates on the wave function, and you cannot just replace the order of derivatives. So I'm not going to prove this, but these are the Ehrenfest laws. Now, they look like Newton's law, but they are not exactly Newton's law. They are a bit different. Someone can tell me why, in what sense? They look very similar, right? It's a bit misleading.
They are statistical.
First of all, they are statistical, but are these at all equations? Are they closed equations? What do I mean by that? Let us assume now a very simple problem that you learned, and that is that, let's say, the potential is a simple spring. This I call a linear problem. So this is the potential. You know everything on the classical solution that gives you oscillating solution. You studied this in high school. Okay, so let us use this equation. Then I have the derivative in time of x is P over M. Well, that's simply the definition of velocity. The velocity is momentum over M. That is like classical, okay. And then I have the second law of Newton. I have here minus this. I take the derivative of v of x. What do I get? K, some spring constant. This is something reflecting the parabola here. So this is the spring constant. Let us assume K is positive. X. Well, this is great. This is simply, you know the solutions of this guy. So you already solved a quantum problem you solved now. Not the wave function for the oscillator, but you found the average position and its average momentum, because the solution of this guy is this simply oscillation, cosine omega t plus some phi, right? Everyone knows how to solve these equations. And this is exactly Newton, right? No problem. But what would happen if this v of x, if this potential would be nonlinear? So let us take now v of x, some kn, x to the power n, for example. what would happen then?
It wasn't linear, but the first one wasn't linear. It was a force well.
It's linear in the force and non-linear in the potential. So when I say linear, I mean linear in the force. Because you know the spring is linear because you solve it always. So you always solve linear problems. But if you have a non-linear potential, then you are a little bit in trouble in the following sense that this will be okay. This will be okay. This is what you are used to. This is, again, velocity is momentum over mass. Fine. But then this Newton's law would be n kn xn minus 1. And okay, when n is 2, then this guy, this is the average x, they are the same thing. But here, you get something which is not this. So, in fact, this is not exactly an equation, because you have it's not a closed set of equations. You have the time derivative of x, you have p, you have the time derivative of p, this guy. But to know what is the dynamics of this guy, you need to take the derivative of this, which is a nonlinear, and that will give you another equation, and so on and so forth. So it only means that Ehrenfest laws give you on average the Newton's law, but they are not solvable equations. They are not simple equations. And to get Newton's law, what do you need to have? So what is the real classical world?
Linearization.
What?
Linearization?
No, linearization is not the classical world. That's the boring classical world. If you want a classical world, you need a wave function which is very, very narrow and localized. That means you have no uncertainty in position. And if this would be the case, then this average would be on some very narrow function, and then this would be some constant x to the power n minus 1, and this would be the same as this average. It will have no fluctuations. So the real meaning of classical mechanics is that you have some wave function that is very narrow and has no width in some sense. And these Newton's equations are fantastic for linear systems. I can solve them. I can know everything about the oscillator. The wave function here, let's say, can be super complicated inside here. I know the average position, how it changes in time, because I know the classical equations, because you are in the linear thing. But this doesn't help you once you are in a more complicated potential, which is nonlinear. So just to summarize again, what we learned was there is more meaning. P goes to minus IH d over dx. And from here, this we know already. So the classical momentum goes to an operator. But now I know how to calculate P, or more generally, P to the power n average, just by taking this operator, putting it to the power n, and plugging psi star and integrating. So the meaning of this operator was extended now. I know how to calculate the averages, and Ehrenfest laws give, I call it semi-classical, that's nearly classical, but not exactly, classical laws. So on average, at least in linear systems, you are just doing what the classical is expecting. So quantum mechanics is, let us calculate the fluctuations, the variability, and which is very important in small systems. Do you want to break now, or do you want to continue to the end?
Yes, please.
You want to break? Good. Okay, so let us have 10 minutes break, and then we'll continue. You have questions? Yeah. Ask.
What does that mean? What's the limit, like, from quantum mechanics to classical physics? I mean, in the average, that means with a lot of particles, I'll go to classical mechanics?
No. What do you mean, a lot of particles? The answer is, very briefly, and you'll see this also in this course, but also in next quantum mechanics too. Essentially, it means that when h bar goes to 0, or when the mass goes to infinity, you will wipe out the quantum effects. We will see this in an example maybe by the end of the next lesson. But that is the real true meaning of quantum mechanics when h bar goes to 0. Now, in reality, h bar is a constant. So you need to define some dimensionless constant, which depends on h bar, and then you can take it to 0. And we will see some examples soon.
No, because I tried to think why the Ehrenfest laws bring us to the classical,
on average.
Yeah, but what does that mean? Like, what does that mean physically? How, in which limit we get?
It means the following, that, as I said before, if you are not, let's say you have a very crude measurement device. The crude measurement device cannot distinguish, your mistake in the measurement is huge compared to the width of the wave function. So anyways, you cannot detect the width of the wave function, and only what you care is more or less the position within a mistake. So that is the average position, more or less. That will follow Ehrenfest laws. That is one meaning, and the other meaning is simply that is what I meant by sometimes you don't care about the fluctuations. Also if I measure your height. If I measure it in the morning or in the evening, there will be some small variations, blah, blah, you know what I mean? So, but if these variations are tiny compared to your height, you don't really, and you don't have a good measurement device, so you cannot see these fluctuations. So, if here I have averages, and many experiments, they actually measure directly the average because they are not sensitive enough to calculate these small fluctuations, and then you will see them. But this depends on the system, but the deeper answer is what I said before. It depends what you measure. It depends what would you like to show is, let's say, some quantity like this. Is it small or is it big compared to your resolution in your measurement device? Yes, and then we will need to calculate this and see how it depends on different things like initial conditions, like mass, like h bar. And then you'll see how the classical world emerges from that. But just wait a little bit, and then if it's not clear, then ask me again. Okay, so our aim is now to describe wave packets, which are linear combination of many free waves, to see how the wave function spreads in time. So now I'm turning on the time, and I want to know if I start with some wave packet, what will happen to it? Will it move? Will it spread? Things like that. I do this for the Schrodinger equation where the potential is 0 or a constant. It's the same thing. That is this is called a free particle. What does it mean, a free particle? It means that there is no potential field, and that means there is no force field acting on the particle. So this is the super simple case. If I had a classical particle, it has no force on it. I give it some momentum. It will continue moving forever with that momentum. That is conservation of momentum. That is, in this problem, because you have no forces, there is conservation of momentum in the classical world. And what we would like to see, what does it mean in a quantum world? So in this case, the Schrodinger equation is very simple. d over dt psi minus h squared 2m second derivative of psi. So I'm solving this in one dimension. So these are to make life simple as possible. And this, as you see, this is the Hamiltonian. This is p squared over 2m, and this is the operator, simply because the potential is 0. This is the simplest form of the wave function. And you remember we actually started with this because we know what are the free waves here, because this is how we constructed the wave function. The free waves, these are, what I mean by free waves are just oscillating waves from minus infinity to infinity. They are simply exponent I kx minus omega kt, and we have this well-known dispersion relation that omega k is hk squared over 2m. We'll soon rederive this, but this was all given. The k squared versus omega k is coming from the fact that you have a first derivative in time here and a second derivative in space, and that's why this dispersion relation is nonlinear in k. Omega k goes like k squared, not like waves, usual waves that you studied. So these are the free waves, and let us just decide what happens when I act with p, the operator p, on a free wave. Well, what is p? It's minus ih d over dx. So what will happen when I take the derivative with respect to x of this guy? I'll get ik out. Minus ih. Minus ih times I will give you 1. And this is just h bar k times the wave. And this makes some sense that when you operate with p on a free wave, what you get is the momentum of the wave. This is momentum h bar k. That is come from the de Broglie relation. So this makes sense. Or in other words, this is another way to understand why this p is what I'm always claiming, minus I d over dx. So you can see it from here if you want to accept this interpretation. This is the momentum, this is de Broglie, so it makes sense to define this momentum operator like that. But this was a side remark. Our goal is to solve this equation. So what is the solution of this equation? Now this equation is linear. You know already one solution, right? This is the free wave. Last lesson I taught you there is a superposition principle. What does a superposition principle mean? I can take many of these waves, add them, and this will also be a solution. So let us write, based on the superposition principle, the solution to this free particle. So what is the solution? The solution is psi x and t is 1 over 2 pi square root integral from minus infinity to infinity dk gk e ikx minus omega kt. That's it. That's the solution. And what does this solution tell you? This is the superposition principle. Do you see why? I have here an integral. But what is an integral? An integral is a sum with small delta k. So I give some weight for the free waves. This was previously, I called it C1 and C2. And you have many of these guys. So G, K can be anything, some numbers. Tuck, 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 tuck. And each one is multiplied by this. And I sum many. And this is still a solution. But maybe you say two things. I don't believe you. So, okay, we will check that this is correct. And the next thing is, what is this GK? What does it mean? This is the two things we want to answer. So let us again prove it. Even though this is obvious from the superposition principle, let us prove that this is correct. So the proof, well, it's simple, right? when I write this, I mean also that this omega k is exactly this one. It's not a general omega k, it's exactly this one. So how do I prove it? But before that, I have here this 1 over square root of 2 pi. Is this really important? No. I could take this and plug it into this function g of k. This is a matter of definition. And you can already guess why.
Normalization.
No, not normalization. This is related to something you had in your Fourier transforms, and that's a matter of convention that you have this and not absorb it here, but it's totally arbitrary. Okay, so let us prove that this is the solution. So what do I need to do? Okay, I need to work again a little bit. Take the time derivative. That is the left-hand side of the Schrodinger equation. And that is equal to 1 over square root of 2 pi integral from minus infinity to infinity dk gk. G does not depend on time. It's some function of k only. K is like momentum. And now I take the derivative. So to take the derivative, I get here omega k I with a minus. I times minus I is 1. And here I get h bar omega k exponent I k x minus omega k t. And this is not surprising because the time derivative is the same as the operation of the Hamiltonian. It just gives you the energy here. You see, I took one component of the energy of one of the waves, h bar omega k, outside. And now if I have the Hamiltonian acting on psi, which is the right-hand side of the Schrodinger equation, which is simply p squared, let us write it, minus h squared 2m, second derivative, because again, here we have only kinetic energy, there's no potential. Well, that is also simply, and essentially we did it already. What will happen here? I have the spatial derivative, the derivative in space. The derivative on space doesn't work on time like before, it works on the position, of course. And what will happen when I take the second derivative? I'll get ik one time, and then I get ik another time. So an ik times ik is minus, and then you have this minus here, and then that will give you 1 over square root 2 pi integral from minus infinity to infinity dk gk. You have h squared, k squared. What is this? This object here is the kinetic energy of one component of the wave, the kinetic energy of one of the waves. Of course, you have to weigh it by gk, so maybe one of the k is more important than the other. So gk might have a very strong component on k0, but not on another k, you see? So you need to weigh it by this guy. And here I have exponent ikx minus omega kt, because, of course, taking the derivative of the exponent, it leaves you the exponent. Now, you see immediately that what is this guy? This guy, from the dispersion relation, this is h omega k. So this guy and this guy are the same. So IH psi dot equal H psi QED. Now, of course, we have to read it in the backward way. You start here and get here. It just means I can guess a solution, and this is the solution. Of course, I didn't really guess it because I just used the superposition principle, and this is obvious solution, so okay, this is a solution. Okay, good, so we have a solution, but this solution is still mysterious because what is this function, g of k? Any idea what is g of k? How will I find it?
Initial condition.
Yes, who said it? Thank you. So if you have a Schrodinger equation, you have the first derivative with respect to time. To solve the Schrodinger equation, you need to use the initial condition. Give me some initial condition. I can, in principle, solve the Schrodinger equation. If I don't, you have any initial condition, then it's a hopeless situation, like as usual. So we need to take into consideration the initial condition. So what is this to do with g of k? So the initial condition, psi x 0. The 0 means time t0. Always my initial condition starts at time t equals 0. So I just write the solution, square root, integral from minus infinity to infinity, dk gk exponent of ikx. Why did I do this? You see here t is 0, so I don't need to write the frequency. I just take this to be 0 because I'm looking now at the initial time. But this is something I know. What is psi x 0? That is the Fourier transform of g of k. But now I can invert it. Because if this is the Fourier transform, then this guy, gk, will be the inverse Fourier transform of the initial condition, 1 over square root 2 pi, integral from minus infinity to infinity, psi x0, e to the minus ikx, dx now. So I need to take the initial wave function, I have to do the Fourier transform and get the amplitude of these guys. And what is the physical meaning of g of k? It is, as you see from here, the amplitude of being in a specific wave with value k. And these are determined by the initial condition. So which g of k is important? If g of k is a peaked function, this will depend what is your initial condition. Okay, so essentially I solved the problem. The solution then, this is a summary. It's only a solution for a free particle. In principle, give me psi x0, get gk, the amplitudes of the different waves that are propagating. This is done by this equation. Let's call this 2, let's call this 1. And then you can get psi x and t equation 1. Then if you want, you can get average of x, x squared, p squared, etc., etc. You can get whatever you want because you have the wave function. If you have the wave function, you can calculate all the averages. I taught you how to do that in principle. Of course, doing the Fourier transform at this stage or in that stage can be a little bit complicated if you have very special initial conditions or very complicated functions initial conditions, then maybe it's difficult to take the Fourier transform, but that is a technical issue. That is, you can solve it on a computer, for example. It's not so difficult to find for a general initial condition this guy, and we will solve one example which will be very simple. Now, I explained what is g of k. I said it's the amplitude of each part of the waves. It's the strength of the different waves that you sum over. But g of k has a more fundamental meaning, and this I want to show you by playing a little bit with the average momentum, still very generally. Essentially what you see here, that this is the amplitude of this wave, that gk is the amplitude of k. So if this is the amplitude of k, how will I calculate the average momentum directly from g of k? That is the question. Maybe you can already think how this will happen. But if this is the strength of the wave k, this guy can be complex. What is the probability to measure wave k? What will it be? You can guess. It will be g absolute value squared. So actually this g of k, this is what we are going to show now, is a wave function or amplitude in momentum space. You have a wave function psi x of t, which is a wave function in coordinate space, in x. And now you'll have g of k as a meaning of a wave function in momentum space, and now some amplitude of finding the momentum k. To see this, let us look now at p average. Or more or less to justify this, let us look at p average. Well, we know already that this guy, I need to calculate this all for the integral, psi minus I h d over dx, psi dx. And I need to calculate it at some time t. So let us plug in the wave function. Well, this is going to be the integral from minus infinity to infinity dx. Here I have the integral over minus infinity to infinity dk. This is psi star. So I'm just taking this guy, taking the star. Here I'll have 1 over 2 pi. 2 pi, because I have psi star and psi, this guy will be 1 over 2 pi. So I have to take this guy, gk, but is it gk? It's gk star, because this corresponds to this psi. E minus kx minus omega k t. Then I have to take the derivative, because that is the momentum operator, because I'm calculating the average momentum now. And then I have another integral, dk prime, this is this psi, gk prime, e I kx minus omega kt. Wonderful. We have here 3 integrals, 1 over x, 1 over k, and 1 over k prime. 3 integrals is way too much. The reason is that each psi is a Fourier transform of this gk times this time-dependent phase, so, okay. So we have to look at these integral, these expressions, and say, oh, what is the easiest integral to do? What is the easiest integral to do? Oh, sorry, this is k prime. Prime. What is the easiest one to do? Well, k and k prime are the same order of difficulty, so it has to be over x. And why is the integral over x easy? Let us look where we have x. We have x here, and we have x here. And then I integrate over x. So what is that? Homework 1. So aside, integral 1 over 2 pi minus infinity to infinity dx e minus I kx plus I k prime x. This is, someone said it? This is a delta function. And delta function of what? You see here, k prime minus k. you can more or less see it if, let's say, k and k prime are not identical, so you have something that is kind of oscillating, and it can be plus and minus. When you, then I'll get here 0. But if these guys, k and k prime, are the same, then I get here infinity. That is more or less the definition of a delta function. But this also you see from Fourier transform analysis that this is a definition of a delta function. This is why you can go from from Fourier space to regular space backwards and forward. This is the meaning of the delta function. Now, if this is a delta function, wow, that is great. Why is it great? Because then I can integrate over one of these guys, either over k or k prime. All what I need to do now is wherever I see, let's say, k prime, what do I need to do? Just put in k, because when I integrate, and then I did two integrals at once. So it's very easy. I'm not doing all the steps, but it's super easy because this integral will mean that k prime. And then you will get another benefit. You see here what will happen. You have minus, minus, and then I say k and k prime have to be the same after you integrate. So what will happen to the time? It will go away, because this k prime and this k, when you integrate over the delta function, will be the same thing, and you have a different sign. So that means, what happens to time here?
Isn't relevant.
It's not relevant. So I'll get here p is something, but it's not depending on time. Is that surprising? It's not surprising because there's no force. So the average momentum is a constant. Furthermore, we studied already Ehrenfest law, so you know that p average dot is equal to the average of the derivative of the potential, but the potential is 0, so p dot is a constant of motion. The average of p dot is a constant of motion, and that's why we expect that p average is a constant of motion. It's just conservation of momentum if you have no forces. So we get p average after we do this. We get integral over dk. Okay, one more thing we need to do is we need to take the derivative, this derivative first. What will happen when you take this derivative? I'll get out here k prime, right, with a minus. So I also need to do that. This action will give you an h bar k prime with the I and the I. So I'll get eventually, and again, if you did not follow exactly all these steps that I did very quickly out of a matter of time, please go over this at your home very slowly, one step after the other, because these type of tricks will continue forever. I do these tricks now slowly, but eventually you need to wake up in the middle of the night and know them. So then eventually I get gk absolute value h bar k. And gk absolute value, you see here I have g star and here I have g. That's why I get gk absolute value. But what is this? This is the momentum of a free wave. A free wave, I mean EIKX. And what do I do here? I integrate k. The momentum can take any value from minus infinity to infinity, and you have this weight function. So what is g of k? So g of k, you can think about this. First of all, it's a positive number, and I calculate here an average through this. So what is g of k? This is the probability of finding, it's the probability density, or okay, I'll write it like this, dk. Probability of finding the particle either with wave number k or with momentum h bar k. I prefer to call it momentum. Now you can say, oh, well, what are you doing here? If you're a mathematician, this is not a proof. How will I complete the proof to show that this is really a probability density? I cheated here. In what sense? Why should you complain?
You said that.
Yeah.
That it's normalized.
Yeah, I didn't prove that it's normalized. I didn't prove that if I look at p squared, I'll get here h bar k squared. But you can do that if you're not lazy. So you instead of doing this, we can do the same here without this operator. That should be 1. That's normalization. Then you will have nothing of this, but it will be very similar. You'll have a delta function, and you see that this h bar k comes from this derivative. So without it, you get this. And that would be equal 1, because that will be equal this, without this guy here. And that is also called Parseval's identity. That is, if you have the wave, it's more general than quantum mechanics, that is, this normalization of momentum and position space are conserved. So and then I can look, oh, you don't want me to look at the first momentum, let's have here 2. All will follow, and always this time will fall out. And this is because you have conservation of momentum. So I didn't prove to you exactly that this is a probability amplitude. So this is a probability, but the proof is the same, so I don't bother. So you can imagine, you can fill up the gap if you really want. So gk, absolute value squared decay, is the probability of finding the particle with the momentum h bar k, more correctly h bar k plus h delta k. So there is a small region, and if I want to know the momentum between two values, I have to take this gk and integrate it between these two values, etc. So what we see from this example is that the wave function is maybe more tricky than what you imagine up till now, and that you have representations of the wave function. What is a wave function? So we can walk in position space. This is what we discussed beginning of this class. And then you have some wave function that we will denote psi x and t. Then you have an operator of momentum, which is minus I h d over dx. And the position operator is x itself. If I want to calculate an average, I take, for example, average of x is psi star x psi dx. But I also have momentum space. And in momentum space, at least for a free particle, I have g of k. This was an amplitude. This goes to a probability like that, and this goes to a probability like that, the same way. What is the momentum in this space? It's simply hk. That is natural, because that is the de Broglie presentation. And you can guess, and you will prove by yourself, what is x in this space? What do you think is x in momentum space? If I want to do something crazy and calculate through momentum space the average position, what will I have to do? I'll have to take the derivative of gk with respect to k. So this will be derivative with respect to, here you'll have derivative with respect to k. You can try and work it out by yourself. Because if I multiply this by x, let's calculate x. I have, let's try and just the beginning of the proof. Then I need to write it like this. Integral from minus infinity to infinity, dk, gk, ei kx minus omega kt, x, because I'm calculating the average. This is the wave function. This I have to take star, right? Then I have the wave function, minus infinity to infinity, gk prime, dk prime, ei k prime x minus omega k prime t. And then I need to integrate over dx. Now you see, how do I get this k? How do I get this x? I can take, instead of x, I take the derivative with respect to k prime. So this I can write, I'm going to put it here, and replace it with the derivative with respect to dk prime. Then I'll get an I. Oh, I don't like this I want an x. So what will I do? I'll divide it by I. But that's exactly the same thing. You see, this is in momentum, so here I'll have a derivative in k space, which will go inside here. And then I'll take the delta function, do all this stuff, and I'll get the same in momentum space. So this is left for homework, or for homework, or not exactly homework, but I guess most of you don't care. Find operator x in momentum space. There is a difference here between this here and this here. This would be my last point. What is the big difference between this guy and this guy here? What, I mean, okay, this is momentum space, this is position space, but what is the difference?
This is a function of time.
This is time independent. This is because I'm solving here only the free particle. Because I'm solving the free particle, the momentum, the average momentum is a constant. The kinetic energy is a constant. The momentum to the power 200 average is a constant. Everything is a constant because momentum is conserved. So the fact that this guy does not depend on time is the analog of conservation of momentum in classical world, and it is more general than classical world in the sense that in classical world you have P average or P, only one thing is conserved. Here the whole density in momentum space is independent of time when you have no force. So it is independent of time, and that is a consequence. That is what I can say is a conservation of momentum when you have no force in the quantum world, that the amplitude of the waves are independent of time. Okay, so tomorrow in the class you will use this thing. You will use it to solve some special problems. I will not. I don't think I have time, but I'll just kind of let you know what are the results so you can think about this a little bit more. And next lesson we will continue with the proof. So, okay, I have now some formalism which gives you the solution. I solve it mathematically, I solve everything. Now you just give me the initial condition and I'm done. What is the physics though? So let us look at the particle, a classical particle with momentum p0. So you know this is at time t0, this is position, this is 0. Well, you know what will happen if I come at a later time t, it will just move. So it was here, and now it is p0 over m times t, it just moved. And the momentum is conserved and it will move forever. Now let us look at a wave function. This is a particle which looks like more or less a Gaussian. And let us first assume that the average momentum of this Gaussian wave packet, so this is classical, and this is quantum. So let us first assume that average P is 0. And also assume that this wave packet is symmetric. So if it's symmetric, from symmetry, it cannot move in one direction and not in the other, right? It has to remain finite. So now I'm talking to you about the most trivial case where, more or less in classical world, the P0 is simply 0. So what will happen to the particle? It has no velocity initially. It will remain in space and not move. That is trivial from classical mechanics. But what will happen to this wave packet as a function of time? It will spread. And next lesson we will study, and you can also look at the books, it will become fatter and fatter as time goes by. Its mean will always remain at one position, but it will grow. It's also true that here I start with a Gaussian wave packet. Why do I start with a Gaussian wave packet? Because this is what I can do easily with Fourier transforms. I'm a little bit cheating. Anything more complicated initially will be very difficult to calculate g of k. So this is a very particular simple example, but something that you can solve completely. So this will become broader and broader. Now, you know this answer, but actually, why does it become broader and broader? What is the real reason for that?
We are losing it.
What? Let's say you were solving the wave equation with the second derivative in time and second derivative in space that you studied previous. What would happen? Will it become fat? What happens to solutions of the wave function, or of the wave equation? They just move. They don't change their shape. You remember this? Why is that? Why is that? What is the difference here between waves? The dispersion, right. So the dispersion here is the cause for the fact that it is moving, it is spreading. While if you have a linear dispersion, this will not happen. So this happens because omega of k goes like k squared. Why is that? Because you can think about this as the velocity. The velocity is the derivative of this psi, is dependent on k. So some elements are moving faster than the other. So you start with some amplitude of the waves, and then they are spreading, and they are not staying, they are not staying with a constant width, but they are growing like this. And this is a consequence of the fact that you have here a nonlinear dependence on k. What will happen if you have, let's say P average is not 0? If P average is not 0, so you have initially some wave packet like this. Now you know something about, this is at time t equals 0. But what will be the momentum average for all times? It will be the same as at the beginning. The reason is Ehrenfest laws, because Ehrenfest laws tells you that the derivative of P as a function of time is the average force, but the average force here is 0 because there's no force, so you know that this will move. And then if this is the case, then this is t equals 0, then what will happen at some later time? So I started here, then at later time I'll still become fatter, and if this is a Gaussian, it will be symmetric on both sides because there's no difference between, and the distance here, so this is position, is simply the average P over m times t. So the peak, if I just look at the peak of this packet of particles, it's moving at a constant velocity exactly like a classical particle would move. Now, what will happen if you have a very heavy particle, or h bar to 0, or m to infinity? This actually, I'm not interpreting exactly what I mean. This you will have to see next lesson. What does it mean? Because what does exactly it mean, h bar? It has units. You cannot just take them to 0.
Is it a constant?
What?
Is it a constant?
H bar is a constant in the world, but I'm a theoretical physicist. I can do what I want. I can take it to 0. I do that in order to check that I get something sensible. I don't do that in an experiment. Unfortunately, God gave us some h bar, which is fixed, okay? But I can think about this. So from h bar and m, you need to define some parameter that is dimensionless. What is this parameter? What else enters in this problem? What will enter is also the width here, which is the length of a width. So we have to construct some parameter that is dimensionless, but intuitively we understand that each h bar goes to 0 or m goes to infinity. We are in a classical world. So under certain conditions, you will not see this. You will not see in the classical world. You will see this going into. So this is t equals 0. It's a very narrow kind of wave packet. And it will go like this, and this will grow very, very small. But no. If the particle is heavy, this will not matter so much. And then if this is very narrow, then so and you don't have a detector that can distinguish your detector is something like this, then for the detector, you will always find your particle exactly where the classical particle exists. So what I'm asking you to do is read in Cohen-Tanuji about wave packets. And if you do it already for tomorrow, this will be very helpful because tomorrow you will have an exercise on this. And try to understand how do you see with your eyes the classical world, the classical limits, all these things. And then next lesson we will discuss this in more depth, okay? So if you have any questions, if not, we will say goodbye for today. And okay, I guess not, you're tired. So goodbye and see you next week.